I hope you're doing okay. This is it. This is week 10. This is the end of the school year. I can't believe it, but it is honestly, truly here. This is the last big assignment I'm going to give. Next week, I'll probably have like a teacher feedback form or something really low key for you to fill out. I can't just give the one I feel like I've given in the past because this has been such a weird semester. I'd love to hear if we continue this next year. What can I do differently? Anyway, as you can see, the topic this week is something called regression analysis. And you might have done things like this. I'm sure you've done things like this, as a matter of fact, both in Math 1, maybe a little bit in Math 2, maybe not in Math 2, but most certainly in science. And I want to talk about what this is. So I'm going to flip through some slides here that I put together. And by the way, I took all these images off the internet. I'm not giving you any credits for any of them. I'm not doing any citations. I don't know where they came from. Here's some data. I don't know what it's graphing. You got an x-axis, you got a y-axis, you got a bunch of data points. Can you picture a line? Can you picture a line that goes right through this data? That's what regression analysis starts to do. It's a line of best fit. And you can imagine we drew a line through this, maybe you'd have a y-intercept of 2.5 or something like that, and it would have a positive slope. So that's where we're headed with this. As a matter of fact, here's another set of data. This is actually based on some scientific findings around lean body mass down here on the x-axis and muscle strength on the y-axis. And as you can predict, lean body mass, as it increases, muscle strength increases. That's exactly what you would expect. It's not a perfect fit. It doesn't form a perfect straight line, but it's a pretty good trend line going up in a positive direction. As a matter of fact, I could graph it. There it is. That is the line of best fit. And I know that's exciting to you. And again, I'm sure you've done this sort of thing. The question is, how do you know that it's a line of best fit? How do you know it's not one of those other lines? Well, it's something called least squares analysis. So here's a simplified version. It has just 6 data points. Ignore the blue squares. You can see there's a point there and a point there. You can see the point there, another one there, and there. So you can see there are 6 data points here. And the idea here is you make a sketch of where you think the line of best fit might be, and then you draw a vertical line from that data point to the line. And you find the distance between the two, and you turn it into a square and you find the area of the square. And then you do it for the next data point. You find the vertical distance between there and the line just below it, and you turn it in and you find the area of that. You do that for all 6 of them, and you figure out the total. Then you add up the area of all those blue squares, all 6 of those blue squares, and that is the total area. And the goal is, and you can imagine as the line moves up and down or the slope changes, the sizes of all those squares are going to change. And the idea is you want to place that line of best fit so that the squares are as small as they possibly can be. That is how you know you found the best line, the line of best fit. And so that there's a ton of math behind it. There's ways you can calculate it by hand, I believe. I think I did it in college, but it was so long ago I don't really remember. I hate to say, but the calculator, TI-84 calculator does it, and Excel does it, Google Sheets does it. There's a simulator in Delta Math that does it for us. So we don't need to know how to do that, but that's the process behind it. Okay, so. So that's one thing I wanted to talk to you about. Another one here is what happens with outliers. Well, look at this thing. It's an outlier way up here at the top. Can you see it up there? Well, look what it's done. If you ignore that, you would never say that this is the line of best fit. The line of best fit, well, it'd have the y-intercept up here somewhere, and it would have the slope would not be as steep, or it'd be a more shallow slope. So this one outlier way up here pulled the whole line of best fit out. So this is an example of how, another example of how an outlier can change the modeling and the results of what it is you're looking for. By the way, we should talk real briefly, and we'll come back to this later. Why do we care about this? Well, once you know what the line of best fit is, you can start to make some predictions around what data points. If you don't have a data point on in your data set, you can sort of guess where it might be. That allows us to make predictions, and we're going to talk more about that later on. Okay, so let's talk about something called the regression correlation coefficient, or just the correlation coefficient. It's in your calculator and in most articles you see, it's R, lowercase r, and it can be positive, it can be zero, it can be negative, but it's always between -1 and +1. It cannot be outside of -1 to +1. Let's talk about what those numbers mean. So here's an example. This says R equals 0.4. That's an equal sign. R equals 0.4. Well, it's positive. It tells me that's got a positive slope up to the right, which means as the data in general, as one value gets larger, the other value also gets larger. As x increases, y increases. 0.4, the correlation coefficient, tells me 0.4 is pretty low, right? It can go all the way up to 1. And that's not very high. It tells me the data is pretty spread out. If R was 1, the data would be in a perfectly straight line in those little blue squares, the least squares analysis boxes. They wouldn't exist because every point's on the line. So there'd be no vertical distance to find the area of. So if R is 1, it means you have found the perfect line. It doesn't happen very often. Okay, let's look at this middle example here where R is 0. Oops, I don't want to go there yet. Where R is 0. If R is 0, it means the data is completely random. There's no correlation. There is zero correlation. That's what an R value of 0 means. And then over here on the right, R is negative 0.4, not positive 0.4, but negative 0.4. The 0.4 again still tells me the data is pretty spread out. The negative tells me that it's got a negative slope, meaning as x gets larger, y gets smaller. They have an inverse relationship. And data like that exists. So it's important to know. The 0.4 doesn't have anything to do with the slope, and sometimes people get confused by that. The positive and negative tell you if the slope is positive or negative, but the 0.4 has nothing to do with the slope. It has to do with how close the data matches the line of best fit. Okay, let's look at some examples here. Here's one. This is a fitted line plot. I don't know what the data is of. You can see all the blue data points, and you can see behind it there's this sort of maroon line of best fit. Over here, it tells me that the R squared is 86.5%. Remember I said that R goes from -1 to +1? Well, this is a positive slope. So really it goes from 0 to 1. 1 would be a perfect fit. This is 0.865, or if I turn that to a decimal, that's pretty good. Now this is R squared. It tells me that R is even higher. I don't know what it is. I can put it in a calculator and take the square root of 0.865. It's going to be 0.9 something. So that's got a pretty good correlation coefficient. And notice that all the blue dots are pretty close to the line. Compare that to this graph. Look how spread out the data is. It's really spread out. And the R squared value is 0.147. It's getting really close to 0. It's getting closer and closer to 0. So you can see that's what the R value means. It talks about how spread out the data is. This has a very slight correlation to it. Now, let's move on to the next topic, because not everything, even though everything you've done in science or in other math classes has probably been a line of best fit, it doesn't have to be a line. Here's one that's a parabola. This is a line of best fit that is degree 2. You could think about these being degree 1, right? This is a linear function. Linears, we know, are degree 1, right? It's got an x. So this has an x squared. So it's degree 2. So this is a second degree or quadratic regression. You can imagine it's a little bit harder to do the calculations for, but the idea is the same. We could make a plot that goes right through all these data points as best as possible, minimizing those little least squares. We want to minimize those squares. So that would be a quadratic function, I believe. Let's look at some others. Oh, here's one that actually the line is in. This is also a quadratic function, and of course it's inverted. It's a negative one this time, but you could see we could still do that and figure out what the R and R squared values are. Okay, next topic. Imagine we've got some data. It's not perfectly linear. This is the same data analyzed 3 different ways. You could do degree 1 or line of best fit, and the data doesn't really, you can tell the data is not a line. It's not perfect. It doesn't. You got points on, especially on the left and the right, like way out here on the left and way over here on the right, that are further away. So this is probably not curvy enough. It's a line. Well, what if we turned it to a simple curve? What if we turned it into a parabola? I don't know if that's really a parabola, but it serves the purpose here. It's got a curve to it. Maybe now it's degree 2 instead of degree 1, and it fits better. The R value on this, the regression correlation, would be better. It'd be closer to 1. Okay, let's look at an extreme value. This is still a polynomial function. Who knows what the degree is? 1, 2, 3, 4, 5, 6, 7, 8, 9. Degree 10. Imagine we did a 10th degree polynomial regression curve, and it might look something like this. And now there's almost no least, the squares that you're doing, trying to do the least square analysis on, hardly exist at all because that curve is so close to all the data points. That's awesome. It's got some problems with it we're going to talk more about later when you're trying to do extrapolation on the data, but this is really close. The problem is calculators can't do this, and we'll talk about that. But you can imagine the math behind trying to do a 10th degree. It's just a tremendous amount of calculating that has to go on. So there's this idea of underfitting versus overfitting. I've got another map of it here. Here's some data. This has, I can't remember what this was. Some of these didn't include the title, but this was temperature. I can't remember what the axes are. I'm sorry. But here's some data points. You can see the blue curve, the dotted blue line, they tell us is degree 2. And the orange one is degree 5. The orange one is going to fit the data points better, and the R value is going to be closer to 1. So that's the advantage of that. It's a better fit for a curve. I can't call it a line because it's a curve. Lines are straight. So, but the problem is it's probably an example of overfitting, and we're going to talk more about that in just a little bit. Oh, here's something that I find interesting, and I was looking at all these curves. This is you can look at the data for coronavirus cases in Italy and the US and all the data points, and you could come up with an equation based on them. So let's look over here on the left. This is linear, by the way. The y-axis goes from 0, you're adding 15,000, another 15,000, another 15,000, so 15, 30, and 45,000 cases. This is from February 18th to March 19th. It's essentially a month, right? It's essentially 30 days worth, a month. And you can see Italy looks way high, right? It's got this nice, it's exponential growth, isn't it? Look how it curves up like that. And then the US too starts slower, but it's starting to curve upward. Italy looks like they're in a much worse position than the US. And at that point in time, we're going to see that may or may not be the case. They definitely had more people with coronavirus than the US did. But anyway, let's look over here on the right. Look at the y-axis. This is a logarithmic scale, which really means exponential, right? They're inverses of one another. This goes from 1, 10, 100, 1,000, 10,000, 100,000. So it's increasing exponentially. So we call it a logarithmic scale. Notice now, and the advantage of this, and some science teachers, especially chemistry, do a nice job talking about how you can change the scale on the y-axis to change the shape of the graph. And this could be really misleading sometimes, but here I can see that Italy is still growing in number of cases, but look at the curve. It's getting flatter. As time goes by, it's getting flatter. And compare it to the US, where it's getting steeper. So I can see that based on these curves, if these curves continued, it won't take too long for the US to outbeat Italy, if that outbeat's not even a word, to beat, and beat's not a good word either, is it? Because it's not like having more cases makes us win. But anyways, you can just by changing the scale from linear to exponential, you can start to see how the curves change. It has nothing to do with the regression, but I found it really interesting. I wanted to throw that in here. What have I got here? Some kind of other science thing. Exponential curve, you can see the growth. They plotted it in there. And again, this was some kind of thing with cells and half-lives, and I didn't get into the details. I just stole it off the internet. Newton's law of cooling. This one, boy, I remember it was like University of Kansas or something like that. They were doing some analysis of Newton's law of cooling, which we've studied. They took 800 milliliters of water and it was boiling at 100 degrees, and they put it at room temperature, and they did some measurements on it over time, and then they found a curve of least the best curve, and it is exponential decay exactly as we studied. You can see the line of the curve of best fit is pretty good. It's not perfect, but it's pretty good. I guess you'd then have to do some analysis about why it's not perfect, but that's an example that I thought we should all be able to understand. What else have I got? Oh, here's one. Can you guess what shape that is? That's right. It's logarithmic. How do I know? It's got a vertical asymptote that's horizontal, right? And then it continues to go up, but at a slower pace. So that is a logarithmic graph. Here's another logarithmic graph. Don't ask me what all those math symbols are, but it starts steep. It looks like there's probably an asymptote over on the y-axis there at 0, and then it goes up. It slowly changes. Oh, this one was interesting. This is more complicated than any of the models we've studied, but I was fascinated by this. So up here in the observed, these are the brain waves of a person that has epilepsy when he's not having a seizure. This here, these are the brain waves while he's having a seizure. Look at it go up and down. Look at the difference in things there. So scientists did this, and then they actually created a model that comes pretty close to what it looks like. So here's their simulated data for normal brain activity and having a seizure. I don't know how they did it. I don't know what the equations were, but I thought it was interesting that people are actually taking the actual data points and then simulating them so that they can do some hypothetical studies in the lab without having somebody hooked up to a brainwaves machine. Anyway, here's one where I feel like I'm talking too long, so I'm not gonna spend a whole lot of time on this. But here's one that follows a sine curve. We haven't talked about sine curves, but it's the form light waves and sound waves make. This is this going from 1995 all the way up to 2017, so it's a little over 20 years worth of data. Seasonal temperature in Madison, Wisconsin. As you can picture, in the middle of the winter, it's low. So it's cold, warm, cold, warm, cold, warm. Every year it goes through this cold to warm cycle. And then he did a line of best fit with a sine wave and came up with this blue line that goes through the data. And then he did a bunch of analysis on that data. And there's some cool things here. One of the things I wanted to talk about is here in this linear trend. I wish I could zoom in. I don't think I can. It says the mode is 0.0682. So that's going from one year to the next. It's 0.0682. That tells me that it's got the linear trend is positive, and the premise of this paper is that this is proof that there's global warming. Okay, because on average the temperature is going up by 0.0682 degrees Fahrenheit per year on average, which isn't very much, but it's warming. And but notice he's got this thing down here. It says 95% HDI. HDI is another way of saying like 95% confidence interval. Where everything is squished into the 95% with margin of error, and it's more complicated than that. But I want you to notice that down here, zero is actually in that 95% HDI. It's in that interval. That means that even though the mode is at 0.0682, we're not 95% certain that it's not negative. So it could actually be zero. And that's an important point here when you're analyzing this data. I don't know what else is in there. There's a whole bunch of stuff in there with stats, and you can see he took all this data and turned it into some nice bell curves. Okay, next big topic, interpolation and extrapolation. So here's some data. You've got all these blue points here and the line of best fit. Nice simple line of best fit that goes through. That happens to be one outlier. We've got the lowest value is here and the highest value is on the x-axis, not the y-axis. We've got the low and the high. All the data, of course, is in between those. You could say that the domain of the data goes from here to here between those vertical red lines. If you wanted to make a prediction in between the lowest and highest that's within the domain, it's called interpolation. And let's say I wanted to find out at 30. If x is 30, what's a good y value? It would go up, and then I would go across, and I would say, it looks like maybe 70 or 75. So if we're at 30, then the y value would be 75. just by going up to the line. This coordinate here is 30, 75. So you can use that line of best fit to interpolate and understand what the data is doing within that range. And that's one of the key things. That's why we do this, so we can make predictions about what's going on. Now, this is when it gets dangerous. Extrapolation is doing exactly the same thing, but outside of the domain of the given data. So either way over here to the left, we're extrapolating, or way over here to the right. For instance, let's say we wanted to find out what our prediction would be is if the x value is 60, what's the y value? Let's see. I would go up the line, and I'd say, okay, well, what does that map to? That maps over here to 125. So if x is 60, y is going to be 125. There must be a data point here, 60, 125. I'm just eyeballing. I didn't get out a ruler or straight edge and measure that, but that's what it looks like. So that's called extrapolation. Now, the problem is, I'm going to go back to, where is it? This graph. Yeah, this graph. Yeah, this graph. So if you're using a curve that's a pretty low degree, extrapolation can be easier and more predictable, right? I can follow this blue curve, degree 2. I know that it's going to continue. It looks like we're at the maximum. It's going to then probably decrease a little bit. Even that makes me a little nervous. But look at this orange one. It changes direction so often. Who knows what it's doing outside of that data? If I went out to 130 or 150 on the X value, who knows? Orange is curving up, blue is trending down. I can't tell. So when I'm looking at, where to go? When I'm looking at data way out on the edges, it's harder and less likely to make any sense. And so extrapolation is, it's okay, but it has to be really taken with a grain of salt. Okay, that's all I'm going to talk about, except I have some funny jokes. Okay, here we go. Here's one. Why is that woman scowling at me? Do I know her? And then down here it says, if she loves you more each and every day, by linear regression, she hated you before you met. I love that. So if she starts off not even like you or not like you, and she likes you more, extrapolate backwards in negative time, she hated you. Does that make any sense? Okay, let's look at the next one, in case that one didn't make sense. Except it's not working. Here it goes. Let's see. Oh, here's a woman that just got married. Yesterday, she had 0 husbands. Today, she has 1 husband. And then this guy goes, as you can see, by late next month, you'll have over 4 dozen husbands. You better get a bulk rate on wedding cake. Again, an example of how extrapolation is bad. It can lead you to bad conclusions. Okay, here's my favorite one. Borderline school appropriate. We're going to say it anyways. So the age at which American women first have sex hasn't changed a whole lot. This is going from 1940. Oh, this is up to 1980. That's not very recent, but that's pretty. It actually gets a little bit younger, but not much. The age at first of the first time a child has gone up pretty steadily. Not as much as having being married, but goes up. Okay, so the idea here is, what if we extrapolate backwards? What if we go back 1940? Let's see. So this line is going to the left. This line is coming down. I think they're going to intersect out here. I'm going to say that's 1925. Okay. In 1920, according to this and according to extrapolation, where women were having having kids before they even had sex. That is not a good example of how extrapolation should work. Anyway, I hope you found this interesting. The one last thing I'm going to touch on real quickly, and if we were in the classroom, by the way, there's a whole bunch of stuff we would be doing. I've got hands-on experiments what we would use to gather data that would go through all this regression analysis on. It was bouncing balls and catching paper airplanes and doing all these things to gather data, and we just can't do it because we're at home. And I would be teaching you how to do some of this stuff on your graphing calculator. These are some screen prints I took off the internet. And there's a whole bunch. If you look over here on the left-hand side here, linear regression, quadratic regression, cubic and quartic regression. Here's another form of linear regression. I've never once used it. LN-reg. Well, that's natural log. That's the natural log regression. And we've got exponential regression and power function. Power function regression. Logistic one, sine, that's like the trigonometric, the up-down sine waves regression. So the calculator can do a lot of this stuff. You have to put your data, you have to go stat edit and put your data in and then go through the analysis. Here's an example of what would come out for linear regression. It would say y equal ax plus b. It tells me what a and b are. So this is the slope, this is the y-intercept. 10.5x plus 0.5 plus 0.1 is how I would read that. My r squared and r values are almost 1. That tells me that the data that this linear regression was based on form almost a perfect straight line. And then your calculator can actually graph it using the stat graph function. You can stat plot. You can plot the data and the linear function, and I think that's pretty cool to do. I think that that shows some real power of what your calculator can do. Anyway, that's all I've got for you today. We will probably have a brief chat next week, and I'll be looking for some quick feedback. But really, folks, we are done. I'll talk to you later. Bye.